Finally, for our last discussion, shear stress. So unlike with tensile stress and bulk stress, shear stress, in shear stress, the force applied is parallel with the resisting area. As we can see in the figure, our forces is this one. At both sides, directed at both sideward, and the resisting area is this one. Just imagine two plates. Let's say you have two plates here being connected by our rivet. Just imagine like that. So we have here our two plate connected by a two rivet. So when a force is applied sideward, so what area resists or which area experience the shear stress? So the area of this rivet. Okay. So for the shear strain, it will be a little bit strain. It will be a little bit different with our tensile and bulk. So because our strain here is equal to x over h, where x is this one, the displacement, the distance displacement of the two faces. Okay? So as we apply force sideward, tendency of the body is be a little bit slant. Okay? Over h, which is the original height of our body, of our object. Okay, and for the elastic modulus, our term for the elastic modulus here is shear modulus. And the symbol for shear modulus is S, which is equal to the ratio of stress and strain. Or equal to force applied times the original height over area times x. So in real life situation, x is nearly always much smaller than h, and also it is dimensionless. Okay, so let's have an example problem. So an object in the figure, which I will draw, is a brass base plate of an outdoor sculpture that experienced shear force in an earthquake. The plate is 0.8 square and 0.5 centimeter thick. So I will draw a square here. And 0.7 thick. Okay, so what is the force exerted on each side of the force? if the resulting displacement x is 0.16 millimeter. So our original height is 0.8 meter. So this is our height which is 0.8 meter. And the thickness, this is the thickness, is 0.5 centimeter. And we're looking for the force. Okay, to solve for force, we will use the formula shear stress is equal to force over area. Which means we have shear stress times the area. But we have no value for the shear stress. So to solve for shear stress, we will solve for the shear strain force. Okay, first. So the shear strain is equal to x over h. This is equal to okay, so take note, our x is 0.60 millimeter. So don't forget to convert it into meter. All over 0.8 meter. Therefore, our shear strain is 2.0 times 10 raised to negative 4. Okay, so now to solve for the stress, we will use the shear modulus. So shear strain times modulus, which is equal to 2.0 times 10 raised to negative 4 times the shear modulus. Again, your assignment is to look for the value of Young's modulus, bulk modulus, and shear modulus of common materials. Okay, so for a brass material, the shear modulus is equal to 3.5 times 10 raised to 10 Pascal. Therefore, our stress is equal to 7 times 10 raised to 6 Pascal. So now we can solve now for the force. So force is equal to area, the stress, which is 7 times 10 raised to 6 Pascal, times the area. And what is our area? This one. Okay, to solve for the area, multiply 0.5 centimeter. Don't forget to convert it into meter. Times 0.8 meter. Okay, so therefore our force applied is equal to 2.8 times 10 raised to 4 Newton. Okay, so now let's check your understanding with this topic. By solving the test your understanding. And this is the figure for our problem.